Well, indeed, there's a perfect examples of pile driving, just for fun. So, i- in fact, in the real practice, what we do for pile driving, you can think of like typically there's like different components where we try to drive piles into the ground. At the pile toe, we have a drive shoe, so you kind of like has have a sharp shape, triangular, so it helps you to penetrate the ground. Um, and it has a hammer to pound on the piles, but in between there's other mechanisms. There's like a pile cushions and also hammer cushions sandwiched in a helmet, what we used to call like a drive cap. So pretty much like you need to those like cushions usually made of more soft material like a wood to absorb the energy. Otherwise, like if you have a hammer directly pound on your piles, metal to metals or metal to concrete, then pretty much like you would damage your pile head right away. Because a lot of energy you can expect, and the hammer is it need to be like a steel. And for the different piles, as we learned from C467, it could be either H piles, which is steel, or reinforced concrete piles. So here's a steam hammer, for example. So you see the piles is here, and you have all these like hammer cap here, and all the cushions, and this is like driven by a steam machines for providing the hammering force. So this way is even much more heavy. So the previous one we saw is offshore. This one is onshore, and you use a diesel power, which is much higher capacity. And when you pounce on the piles, you see like how big a hammer can be. So this is the piles again is a hollow steel piles and with a pile cap here and the cushions, and you see like there's a lot of force to generate like to the piles, which like type a different method or what kind of hammer we use. It kind of like our scope for this class, but like it's kind of like an art of geotech design. You need to find or like you need to calibrate yourself or before you drive the piles. Pretty much you need to do all the engineering analysis based on your soil profiles, like the varying capacity of the soils, and like whether you're hitting the bedrock. You should know all those informations such that like what type of hammer you need and what kind of capacity of loading you need, because you cannot like overdo or underdo it if you like way overestimating the capacity of your piles and also like the reaction force provided by the soils. Then you could over driven it, and you could like damage the piles if you are over driven your piles. If you under driving your piles, what happens is you have a hammer that like much smaller than like what you need, then you cannot penetrate the ground, and you just have a small hammer and then like pounds on the piles, but the pile is not moving. So this lecture we will talk about some basics pile driven pile design, because this is a really advanced topic, and even beyond like a class like this, this just hopefully to get you started. And this class, this lecture, where we talk about different piles, we talk about some simple method on how to find out the pile capacity or estimates the pile informations based on the different piles informations that you measure during the pile installations. So we get it there. And we do very long piles. You see, like, especially like, you have a very real fancy project like a high-rise building. You need to have a very deep foundations, go all the way to bedrock, go over a couple hundred feet. Then we will keep extending the piles, and so we will do the welding on site, right on site. You keep driving sections and sections, and when you're close to the end of one segment, and then like you do the welding right on site. So geotechnical engineering, we take care of the offshore structure foundations too, which is the 80s and the 60s to 80s. Those was the golden age of the oil industry, and now maybe we start shifting to renewable energy, like building offshore windmill foundations. That will be another like a monster, and a different type of challenge. We may not go to deep sea, those like near shore windmill project, like you will have foundations at different soils, where likely maybe like a dense sand, rather than like go to offshore for the deeper and deeper seabed for the oils. But anyways, like 2 or 3 decades ago, it used to be the golden age of geotech engineering in the oil industry, and we built tons of offshore foundations in the North Sea, between Norway and England, and also the Western Australia, and also the Gulf of Mexico, at Houston, near Houston. So there's a lot of fancy offshore geo platform to build. And here's one example. So here's you have a geo platform, but in order to get the oil, we need to stabilize this platform, and we need to drive the piles in offshore environments. That's another challenge. So you see the crane there, like this is foundations platform with four support that you're going to drive pile through it. So we will lower this like kind of like platforms to the sea, to the proper locations, and then those are the piles that we're going to drive. So it's very fancy, super long steel piles. We lift it up. There's this one is up to more than 100 feet. I think it's even 100 meters. And we kind of like install those piles like on our geo platforms, and we will do the pile driving at that point. So what we try to learn in this lecture is through those dynamic poundings, dynamic like driving of piles, and we try to retrieve the informations we need. So remember back to our undergrad class where we talk about axial capacity of piles. We use those statics method, the alpha method, beta method. Those give you analysis results. But think about it, when you drive a piles, you are getting all the informations, the response of the piles and the blow counts when you're like pounding on the piles, and those informations actually can help you to confirm your design, or like give you additional informations. So that's why this like a different piles is another huge topic in deep foundation designs. So it can complement with the static method that we have learned alpha and beta, or sometimes this even can better. In scenario like this, offshore environments, it's really hard to get a soil samples, or like do geophysics or whatever, do site characterizations to know the soil properties deep sea, because we are talking about water, or like depth of the water until you get the seabed could be another 100 meters, and the best chance for us to get the response of the piles or get the information of the more accurate information that we need, could be like in this doing the pile driving. So when we do a install piles, it helps us to confirm like whether our sort parameters is correct or not, or like help us to do a pile of piles, and then you help us to figure out what should we do, or calibrate ourselves for the rest of the piles. Because for a structure like this, you need more than, for sure, you need more than just a few piles. You need a couple piles. Could be sometimes like you have a couple platform, and to support like a one dry and like a drill bit, and then like you have dozens of piles installed, and driving your first piles and then get the information you need can help you to calibrate yourself on the engineer design for the whole platform. So this is pile driving, and that's what we try to get to for this lecture. And again, like you don't want to overdrive your piles. If you overdriving your piles, you have like a hammer is too much for the soils. I mean, like the soil is too strong, and also the hammer is too big. Then you could be happens overdriving the piles. You really don't want this to be happens. You can also fail the concrete piles too. So again, like a failure of precast concrete piles, if like we didn't do our job properly, like this could happen. Okay, so pile driving formulas. So in the early days, to analyze what happens when to the piles when it's just driving, you start with some basic assumptions. First, you assume that the body of the piles is rigid. So first, you start with assumptions. Assume it is rigid body motions. And based on energy conservation equations, they come up with this formula below. So which is the ultimate pile capacity. So here is the ultimate. And this is under driving. So it is different than the static pile capacity. So the two can be very different. The dynamic one, which is the capacity during driving, versus like a static loading capacity, because you are under different loading mechanism. Under static loading versus when you keep pounding on the piles, you are giving like a different loading mechanisms, which end up you could have a very different ultimate capacity. So this term times the S, which is the penetrations of pile. So the L time S here is pretty much just from the energy size of the piles. And the W there is the weight of the hammer. You have the weight of the hammer times the H, which is the job height of the hammer. So W times H is pretty much the energy of the hammers, which is equals to the L times S, which is the energy from the pile setup. So the two are equal each other, which means the conservations of energy. So that is the very first versions of of power equations, very simple, but it comes with a lot of shortcomings because it is not reflecting what really happening for driving a piles. First, the shortcoming of the equations is you must have energy loss. So energy is not conserved. There's a lot of like different kind of loss. You lost from the sun, right? You remember like when driving piles, how loud it could be, and also you lost and a lot of energy to frictions when you're like pounding the piles. There's friction loss to the soil, and also there's a lot of friction loss when you have the piles pounding on the helmet, and also the pounding on the cushions. You know, the cushions, the wood cushions over there is means to absorb some of the energy. So such that like there will be no direct contact, metal on metal, and that over there there's a lot of energy loss too. Second, the pile is not rigid. It's not a perfectly rigid body because you're under a very high stress loading. So no matter what, the piles will compress elastically, or maybe even not when it goes to failure. And also, uh, that's it's not like I think rigid, which means like it's not like a one-way kind of penetrations. So if you think of this like so you assume like going down is positive. Uh, what happens when you're driving to piles two times? The displacements when you pound on it, when you the hammer is loading on your on the piles, and you will go like this. So there will be a rebound. So pretty much like this is the the penetrations, and there are also a rebounds parts too. So the piles pretty much will go down and then go up, go down and then go up a little bit, go down and go up a little bit. With end up the net is still going down, but like the pile is kind of like a little bit like a very stiff spring. When you press on it, it will rebound a little bit. When you press on it, it will rebound a little bit during the driving process. So that's what the simple equations over there cannot capture, which means like the proper way to mathematically model or mathematically to describe the piles is not like a single energy formula. So this doesn't work. But the wave propagations we'll talk about next is a better way to describe the actually the how the piles behave, because when you loading on the piles it's actually is sending a lot of like a wave, because we P wave, primary wave, compressive wave, down to the piles. So if we can use particles, like pile particles, wave propagations formulas, that would be much better than a single energy formula to describe the phenomenon. So that's what we're going to talk about next. But here, like let's look at the basic formulas from the early days, um, and also what we are doing with those like energy formulas is we are describing the dynamics, ultimate capacity, but it is not the statics capacity that we may want to investigate. Because during the pile driving, yes, we are sending a dynamic loading on the piles for the driving purpose. But ultimately, why the piles is there is because we wanted to sustain the static loading from the structure, uh, which is static loading connect to the the static loading come from the column of the structure, and that's what the piles need to be. It's not just for the driving purpose. So those are the shortcomings of those pile driving formulas, those simple ones. So in light of that, there's another versions of or improve the of computations like the second formula is over there. So does it improve the one? So make some slightly change. Um, so it has effectiveness. So this is the efficiency uh, factors to try to capture the energy loss. And in light of the shortcomings that we mentioned about, then now it has second terms. So this is the elastic rebound that we talk about here. And another improvement, or make it more practical, is the formula below. So which try to represent the penetrations by the number of blows. So this n here is equals to the number of blows per 300 millimeters penetrations. So making it more practical is just by setting like a certain interval, and then which is 300 millimeters. So every advancements of 300 meters, they keep counting on number of blows um, for the from the pilot driving. So they can set up. So now you have the R there, and then you have the N there, which can be easily set up the R versus N curve, and based on the shape from the based on the equations, we can get the this kind of shape for the mathematic expressions, and the asymptotes will be the maximum value that you can get, which uh, when the n becomes so large. So this the first term at the bottoms drop out. So the maximum will be the dynamic driving capacity of the piles that you can get. So with this, this our end port, mathematically is nice because this equations pretty much is so the curve here pretty much is representing these equations. So uh, if you're recording the end, and then the efficiency of the piles, then pretty much you can roughly estimate the dynamic capacity of the piles, or you keep recording your data, so you have, or you keep pounding your piles, and then to a point that you reach the maximums, then the R, and then the N, then now you can estimate the efficiency of the driving process. So, but the big picture here is like what we learn out from this is those simple form of pilot driving formulas is a is simple. It's a good starting point, but you cannot like answer all the like the shortcoming here that we talk about. You know, the very first versions of the equations, you didn't talk about energy loss, even though we try to capture it with the factor of efficiency here, but it's still like not fundamentally like looking this problem correctly because still didn't answer the part that the power is not rigid and also is not answering the part that actually we this is a wave propagations phenomenon, but not like conservation of energy like uh, setup, and also is just not able to tell the informations of the static power capacity. So we need something more advanced to look at this complicated issue, which we will talk about the wave propagations analysis. Propagations. So if we look at segments of the piles, so we talk about the how wave propagates through a piles in terms of velocity, and this is useful for finding the piles informations during the dynamic driving. And this method, this like a wave propagations method, is found to be more reliable than the other piles driving formulas that we talk about in the previous two slides. So using like a more physics, so this is like a more physics based, can get around the shortcomings that we have, like the because now we're looking velocity rather than like a global energy. So we talk about how the particles actually is focused on how the piles particles propagate throughout the driving process, power driving process. So in a way, like this is more fundamental and also more science based, which will give us more accurate results. But like again, like there's some assumptions going on, and then another trade-off is require much more computational power and for engineers on the basic understanding on physics and math. You need to deal with differential equations, and nowadays like many computer software that are capable to package the capable to solve all these differential equations, and other presentations I upload on Canvax by practice engineers from the ISSME, the International Saw Mechanics Associations. They give presentations on this topic quite nicely, and then they introduce like some software package over there. So feel free to take a look, and in practice, where likely you will use those computational package, which is not cheap. And but if you work for a geotech firm, they should buy the license. But but what being we are doing here now is hopefully like we go through the derivations of math and also helps you to understand what's going be behind those computational software. Otherwise, like without really knowing the basic or at least like what's going on, then you will be just like a click and run the software, and that could be very dangerous with the like understanding the fundamental of the fundamentals. But anyways, like my hope is like walk you through this wave propagations math durations, and we'll do examples together uh, with hand cal. So with a very basic examples, walk you through like not only setting up the equations, but numerically how to solve those problems. by hand. If you can do it by hand, then like you have to see what being behind the black box, um, and hopefully like in the future, when you do the practice when you're using software, you knows like what's going on behind. And because this is wave propagations, so they need to use a finite difference approach, which means like a time step approach for pile driving problems. So it's not finite elements approach. It's like this is a finite difference approach, which is very similar to, which is the same framework, being finite difference that we use in geotechnical engineering, the software FLAG that is very popular in our practice. So FLAG, is more finite difference program is more general for geotech applications. So for sure you can handle piles problem design, but like for pile driving piles particular design, like you have its own software. So anyways, like now we will talk more when we get to there, but now what we're doing here is focus on the basic setup of wave propagations on a piece of piles. So with piles that with segments of small length of dz right there, we know the stress adding on it from 2n. So we have sigma stress, and then after going through small segments, you can think of like when we uh, heating the pounding the piles, driving the pile from the tops. So you will create the shear wave, um, the driving wave in terms of velocity. I think the better way to draw it is kind of like a wave that go from the top to the bottoms. So whenever like you transfer travel a tiny bit of distance, then the stress will change, and this change here for small segments of dz now is d sigma, and we set up our coordinate. So it's this traveling velocity. The particles is traveling. So there's many small particles traveling through the piles, and because piles is making with many small particles. And well, let me do a better job on here. So, whoops. So with distant u, you will change with the depth and at the time. So the way that the pile particles travel through the piles, the way that particle transfer is depends on the depth and also depend on the time. So is a function of z and t here. And also we have our side shear because the piles is jacking along with the soils. So we have the F here, which is the friction force, which we call it the soil behavior. These are functions of again like the depth, the particles. So the U here is the particle displacements, right? So how the piles actually is moving at a very small scale. Um, and the we know the U. Then if we differentiate that, then we got the particle velocity. And if we differentiate one more times, we got uh, the 2-second orders of differential equations that give you the partial accelerations and the constitutive models of the piles, which is perfectly elastic here. So we have the perfectly elastic piles, which means the pile stress strain behavior. So this is the strain, this is the stress, it's perfectly elastic, which is described by the elastic modulus E right there. And the strain in the piles will be defined by the epsilon. Epsilon equals to du dz. the change of the vertical directions of the piles displacements normalized by the change of the vertical directions, the z. And we have counter force, right? Or like this is Newton's second law. Overall, the movement of the piles is the mass of the piles times the accelerations of the piles. And if we do our the Newton's second law, F equals ma, and the force that we have, the A is the area of the piles, so the upward force minus the downward force, and then plus the sine frictions, and this P here is the perimeters. So we have the piles perimeters times the side frictions, and then times the vertical segments. That gives us the side shear force. So this is like our force equals to the mass of the piles, and the mass of the pile is the density of the piles times the area, pretty much times the dz. So here A times dz is the volumes, and this gives us the mass of the piles, and then times the accelerations, which is of the piles. We differentiate the displacements 2 times, then we get the accelerations. So F equal ma. And also we consider constitutive relationship of the piles, which we use the elastic, the perfectly elastic model to describe the stress strain relationship of the piles. So the stress will be equals to Young modulus times the strain. So which is the Young modulus of the piles times the strain will be du dz of the piles. And the side shear, so the side frictions, will be equals to functions of the depth, the pile displacements, and also the time. So this is the soil behavior. And if we combine the 3 equations, then we give us this differential equations to describe the wave propagations during the pile driving. So again, like the E here that we talk about is the pi modulus. And this particular terms we talk about, right? That is the pile accelerations or the pile particles accelerations. So this equation here pretty much is the governing equations of the wave propagations. So if we want to find more pile informations like during it driving, pretty much we solve for these equations, and the computational package software that you use for pile driving, pretty much like they sell a finite difference approach to solve for this like a second order differential equations to try to capture the physics behind pile driving, treating like the piles is moving in terms of a small displacements, and it change with the depth and also change with the time. So that's why it's differentiated by the dz, and also differentiate by the dt, and capturing the soil uh, uh, behavior on the third terms right there. And if we try to simplify these equations, if we try to just like focus on what being uh, more like a controllable or more like able to solve on a piece of paper, um, we assume the compressions, wave propagations, or you propagate through a piles without um, surrounding soils. So what they do here now is assume there's no soil, just we just pounding up piles. It's not physically correct doing a pile driving, but like we what we trying to here do here is just try to simplify uh, the scenario, making reasonable assumptions and just look at how the piles behave. So it's not correct, but at least like we want to see what actually happening. So pretty much it's kind of like doing experiment in the lab. I understand that there's a conservatism behind, but try to understand the fundamental physics before we add on more complicated components. So that's what people do, or the academic um, uh, well, mathematicians do at the first step. Take away the complicated like terms, but being like a reasonable being try to simplify some terms, and then let's look at the physics and what happening. So if we make that assumptions, then pretty much we drop off the third terms here because now we don't have the soil, the side shear, and this equations pretty much simplified into two terms only. And if we make further like transformations for this differential equations, so we assume x equals to this terms, and the transfer functions equals to this terms. So here, what we're doing here is just purely mathematics. We play around with the differential equations by making some substitutions to simplify the terms or the equations with mathematical terms, but not like really like changing anything, but just play around with the terms, and then like we substitute x and y into this two term second order differential equations, then this equations now. So this double star equations becomes a much simple form with the two transformations terms that we have made. And then here we realize and we solve for this, the pi, because at the end of the day, what we interest most is the U, right? U is the pile displacements. So we fundamentally we want to understand when we drive the piles, how much movement is the piles. And we set up the differential equations. If we're able to solve for these differential equations, then we can solve our problem because we can mathematically model how the uh, piles behave moving upward and downward when we driving the piles. And now, like we make the simplifications, and then we take away the soil behavior terms. Then we get to a very simplified equations. And if we solve for these equations, these differential equations, then pretty much we have two functions. And those functions, well, if we undo our transformations,
So that's the beauty of using transformations in differential equations. Remember, like how the differential equation cast, the calculates some forecast, maybe some while ago. So after all these transformations, they help us. At least this is again, this is not like perfectly correct because we sacrifice the accuracy by making simple assumptions, but at least they give us some idea what's going on. So the displacements will be depends on these two functions over here, and we understand when we drive a piles. So this gives us like the displacements, given ideas how the piles would behave, and when we drive our piles, right? So at like certain locations, depth at time t versus like locations that is like a further down. So with travel distance of delta z, and then at time plus delta t. So if we like make use of like the time steps here. So another concept here is very important when we solve for these differential equations. We want to use time steps. So next we will do examples to see how numerically well we can solve for those equations by considering time steps. So now we have a time steps of delta t here by traveling like a small segments of the piles. Um, and if we want to find out the velocity, the wave velocity here, uh, the wave velocity, we call the C here, in fact, is the change of the displacements divided by change of times. And this is the wave velocity. And like, if we consider time steps here, so this is the U, right? The U, uh, oops. So the U delta, the U T plus delta T minus UT. So pretty much it's like, how much displacement has traveled with a small delta t, right? So how much displacements go down with small time steps. That's what this means by using these equations. And if we do the math, we find out that delta z will be equals to E over density derived times delta t, and the wave velocity will be equals to E divided by uh, the density of the piles. So we can like simplify the wave velocity in terms of the material properties by making some like assumptions to get there. So what we're doing here is just we try to physically understand what's going on, or like walk you through what is the physics behind when we try to do our wave propagations and the problems of power driving. Next, we will try to do examples, how try to make use of this framework or the wave propagations to model piles, actual piles, driving piles, and using finite difference approach by hand to walk you through how to work out the math. Okay, now let's talk about a numerical approach to solve for the wave propagations problem in a piles during a pile driving. So what um, engineers has done to tackle this problem is they discretize like the piles into different many segments. As you can see in the picture, when you have a piles, you have different components. Actually, I'm talking about pile driving. You have different components. Of course, you have the piles, right? So you have the piles components, and also you have the hammer. So the hammer can be a diesel type of hammer or like a uh, steam air steam type of hammer. Uh, and then you also have the connection part where the plate, the strike plates, the cushions for the hammers, also the cushions for the piles, the helmets. So that's another like a segments for the piles, and all this three comes together is the pile driving mechanisms, and the discrete uh, discretizations help us to use finite difference approach to solve for this wave propagations phenomenon. So what it does, for example, here now, it has like a three, at least like a three parts. First, you have the hammer part. You need the weight, and also you need the stiffness of the hammer. So that's the first part. So we break down into little different parts, and also you will assign material properties for that. And the another basic part is uh, the part that connects the hammers and the piles. So all the other stuff like the hammer cushions, the pile cushions, the striker blades, and the helmets. And with that, the same thing. You also need the weight and also the stiffness to describe this part. And last but not least, you have the piles, which you need like to talk about the weight of it. And well, when I say the piles, I better just include the part of piles, excluding the pile toe. So this is the third part of it. And here is your pile toe. So which you would describe that by a QC curve. Remember like C467 when we talk about the TZ analysis at the toe, you can model as like a spring. And all this like a piles is like we discrete it, and then your model is with the weight and also like a spring, so like a weight attaches to a spring, and the spring have its stiffness. And for the piles, so case you have the soil response, so also have this soil side frictions. So that's why like you have the damping effect of soils. So that's why you have the dashboard and also have the spring to model like the soil behavior. So that's how we do. So we break it down into many little parts, and then like from each elements, and we assign the weight and also the stiffness for it. And now, basically, I only break it down into three different parts, but actually, within each part, you need to further break it down to more and more elements, and how many elements you need. The more you have, the more accurate your numerical analysis will be. Uh, and when you're doing computer programming, then you will break down into many. Pretty much you need to iterate to find out the optimum number, right? If you break it down to n versus n plus one number of elements, and then the results is about the same, which means the results will be smaller than a certain tolerance, then you call it good. Just like a settlement analysis, the number of layers that you need to break down, right? For example, like if you break down into 500 elements, you got like pi wave velocity of 0.001 millimeter per seconds. And then when you break down into like a third mole, like n plus one mole, you can still get the same results. Then you call it uh, the number of elements is small enough to be acceptable. Uh, but if you just break it down like we do now, just three big parts, then like this is too coarse, and I don't think the result will be accurate at all. But for the examples, we only break it down into three minimal parts, and then we can do a hand count, And but when a computer doing, for example, the piles, at least you will further break it down into many different piles. I mean, many different elements. Because remember the wave that we talk about, uh, it has the dz terms over there. So which means like the properties of the pile displacements highly depends on the displacements. The further you go down, the soil behavior, and also which is like all those like a dashboard over here, and the spring stiffness over there, you will change because the further down you go, the stronger the soil is with more confining stress. Um, and like those parameters of the so each spring it has its own stiffness right there, and those stiffness and also those like a dashboards like uh to represent the damping of the soils need to be updated. But for anyways, like for the examples that we're going to do, we will just base on three elements as minimal to so that we can do a hand cow examples. So so how the numerical analysis work is we look at different issue or different like wave propagating informations within the piles during the pile driving. The first thing we want to look at is the displacements of the uh, piles particles. So the displacements of the piles, whoops, at a certain time step. So this m here is the mass number. So for this example, if we break it down into three parts, so this will be M1, this will be M2, and this will be M3, because we only look at three parts. And like, for a computer, you will break it down into many parts. Like, within the piles, you will maybe 10 more parts. Then you'll be M4, M5, M6, M7, whatever going on. So those are the mass number. But for the examples that we're going to do, M1 means the hammer. M2 means the accessory between the hammers and the piles, and M3 represent the piles, the whole piles. And the T here is the time steps, the time step. So this time step here is the same thing we look at like the dt in this formula, and then like we also like in this equations. So the time is at certain times steps of the pile particle traveling at. And then like the next time step will be t plus delta t. So that will be the next time steps. And for the next time step, you need to know like how small the delta t is. So the delta t recommended by the original author for this wave final difference like solving approach, he recommends the delta t equals to the delta L, which is the length the length of the elements. So this case is the whole piles, but like in real computations work we do is each like elements that you have. So this is kind of like the delta L right there, divided by the modulus divided by the density of the piles. So that is the recommended time steps that you do. So which what we are doing here is numerically, we look at like a small segments of the piles and see how the informations, how the status of the piles change. So informations number one we are looking here now is the displacements. It's the displacements. So the displacements will be equals to d. So the displacements of the current like mass and the current time steps equals to the displacements of the current mass at the previous time steps plus the velocity. of the current mass and also the previous time steps times the delta t. So the delta t will be computed by this equations right here, or E determined. You tell the computer to do this. This is our recommendations because the time steps you cannot be too large. You want to be the time steps as small as possible. But if you make it too small, there will be too much computation power. You will freeze your computer software, or like if you do a hand count, it will become insignificant. So this delta t, is recommended by this formula over here. This is the minimal time step as small as you need to have a reasonable analysis. So this is the displacements, you know, uh, solving for the displacements based on the informations that you have. Because like the velocity, you can find that out by uh, the drop hammers. Because the very first, because this M here, if you think of an M1 will be your hammer, and then like the very original time steps will be the when you drop the hammers. So that one is easy to find, easy to measure. Actually, this is the information that you or like you can get because you're controlling the hammer. So the velocity of the first impact of the piles, everything starts from there, and then based on the velocity you have, the time steps, and then like you can start able to calculate the displacements. So you base on the displacements of the pyrrole steps, and the displacement of the pyrrole step at the very beginning is zero, right? So we will work through examples and we see a hand count and we see how things work. So that's just the displacements. Uh, the first informations you want to find out for your piles during pile driving, and then we have the compressions of the spring because we discrete our piles or like the pile driving system into many different spring. So each element has its own spring, and the spring will be you see here is equals to the displacements of the currents mass and time steps minus the displacements from the next mass and at the same time steps. So the difference between the displacements of two uh, uh, connecting elements or sequential elements, so the difference between the two elements will be the compressions of the spring. So physically, that makes sense. And the force, the next informations you want to find out from the piles through the wave propagations is the force in the spring. The force of the current mass and current time steps is equals to the compressions times the stiffness. So this K here is the current mass. So the stiffness of the spring. So you have the stiffness for the hammer, the stiffness for the accessory, and also the stiffness for the piles. So each components or each element within each components has its own stiffness, and then you will keep updating that. So everything is based on like the elements and also break down into different time steps. And this analysis method, the next part is you want to find out the soil resistance. Remember, like fundamentally, when we talk about the wave propagations, uh, we have a soil behavior part. So the nice thing about this numerical analysis approach, it helps you to also discreting the whole piles. It helps you also solve for just these piles, solid piles interactions. So this is the nice thing about this wave propagations. It helps you to to break down your piles and then find all the information you need. So this is what a computer think like, or how people program it. So hopefully going through those examples is quite a little bit tedious, but it helps you to better understand how computer program or how people code a computer program behind it. So next time when you use a computational package, then you'll be feel more comfortable with what's going on. So you'll be the engineers knowing all the physics and knowing all the setup behind, rather than just pull a software and then try to follows all the steps and click all the buttons and then find the answers. That's not uh, very like a sound engineers. But engineers should understand what's everything's behind, or at least have a good idea of what's going on. Otherwise, you can be quite dangerous because if you just follow uh, the procedure or whatever, of a software, you could be very dangerous if you go in the wrong directions and you don't know what's going on. Or some very basic, how should you set up the time steps? You know, why this time step makes sense and why this time step doesn't make sense. And how is the design scenario, or how is your computational package modeling the whole thing? Why is always there's a stiffness terms over there? Now it hopefully makes sense to you. Or fundamentally, should you use finite elements or finite difference when you solve for different uh, design problems? Those questions will pop-ups come to you, and very likely, before you get a job, so you will get challenged from your peers, from your clients, or from the prime to ask you those questions. And hopefully, going through all this, we will all have a better understanding of how things work. So for the soil resistance, it make use of a framework of the soil resistance of the dynamic resistance. So resistant here. So this dyn means dynamic is equals to the resistant static, sta here means static, with a corrections of the statics. So times this factors. So it's this J here is the damping coefficients. And this here is the piles particles velocity. So it kind of highly depends on the damping coefficients. And your textbooks has some recommended values for this damping coefficients number to use based on different soil types. So if you go back to your bio textbook, so here if you go back to your bio textbook, you find some recommended values for the damping coefficients J there, based on clays, silt of sand. They have this difference damping values for you uh, to pick from, and based on different reference. So there's an Lowry 1967 reference, and there's another more updated reference 2012, and give you difference a J values to use. So this 2012 reference is from the WEAP manuals, which is a very popular reference for pile driving. And based on whether you have have a coarse grained or fine grained materials, then you have different J's values, the damping coefficients to use. And the V right there is the power particles velocity. So based on these formulas, we can go ahead to find out the soil resistance based on time uh, discrepancies, like or like this finite difference approach. And we are using here now, so this resistance at current mass and current times will be equals to the displacements of the piles minus the D point. We talk about what is it, and then times the soil spring. So pretty much is the displacements times the springs, the soil springs. So this is the static parts. Oops. So this is the static parts, and then times the following terms, the coefficients, the damping coefficients, which we can find on the tables that we talk about, and then the velocity of the piles is a functions of the current mass, which is like the velocity is depends on which uh, mass or which like element is talking about and what time steps, and based on the previous time steps. So that is the soil resistant part. D pi terms. So the D pi terms is depends on like how much the displacement it has mobilized compared with the toll. So remember, like you act like a QC curve. So if it just has been fully mobilized, we call it like the displacement at the fully mobilized level to be quick. So if it has fully mobilized, then this T prime terms will be equals to the displacements beyond the quick. But if if we just not having fully mobilized, this terms will be equals to 0. So that is the terms right there. And last but not least, then the last piece of information will be the velocity of the piles or of the elements of the piles. So the velocity will be equals to the velocity at the previous time steps plus the force we're working on from the previous elements current time steps minus the force at the current elements current time steps, and then minus the soil resistance. So try to work out the resultant first, the resultant force here. So this take care of the soil behavior, and then times the g, which is gravity, the time steps, and then the weight of the soil elements. Sorry, the weight of the pile elements at the current mass or the current elements. So that is the velocity of the piles. So this is kind of like a discrete wave from the wave propagations analysis based on how you divide your piles into different elements and also different time steps. So always remember uh, the way it works is moving from elements to elements, time step to time step. So you need to really understand which elements are you talking about and also what time steps you talk about. And we'll work on examples, and then that will help you to understand the math behind. Hopefully, doing all this will help you to see or to understand what a computations like a package or program would do for the pile driving analysis.
Well, in the recap, the wave propagations method, also using the fine elements approach, is kind of like modeling a horizontal bar with this is just kind of like put your foundation sideways. So kind of like when you're driving the piles, it's kind of like you set this up in the lab. You have a bar, could be a concrete bar or steel bar, and then your pungs. You give like an impulse. You pung on one end, and then imagine you can have all kind of instrumentations in the lab you want. Accelerometers would be very good use in this simple experiments. And then you can measure all the informations like the accelerations, and then you integrate, get the velocity, and you attach the bar by the spring, which kind of like mimicking the soil response, and the bar you have its stiffness. The materials like the metal have its properties like the modulus as a stiffness, and then you could model it as different many different spring. So that is the wave propagations setup. And in fact, if you look back on the history of this type of analysis, it started from many years ago, more than like a century now, about a little bit less than a century now, starting from 1931. Someone originate the wave equations, and then Fox in 1932 present the closed form solutions, or the exact solutions for the wave equations, without much computations capability in those old days. You don't have a computer, and then first engineers start to apply these wave equations to in the applications of geotechnical engineering or civil engineering. Back in 1938, that should be starting Terasaki time already. So the birth of geotechnical engineering is already there back in 1938, and people start to look at applying this wave equations to pile analysis. In 1955, I guess this in this, even though people think this is the best way to go for pile driving analysis, but with still much computational capability back to old days, is not quite popular until in the 50s start able to use computer to carry on a lot of iterations or solving differential equations. So the first computer code was developed, and about in the 60s. So I believe this is Texas A&M. So Texas A&M University started to work for TxDOT. So Texas Department of Transportations started to look at this more intensively, and then start to work at Case Institute to develop the first still quite popular computer program called WAP. So by this guy, Wash. So he is the one that who give the lecture for the International Soil Mechanics Society, which is his lecture on pile driving is recorded. It's also on Canvax, so feel free to watch it. So he has been working on this topic for more than 50 years. So there's a lot of wealth of knowledge over there. And Davidson's at Illinois, I believe it's at the campus of Urbana-Champaign, start to work on this more from the computational side. And nowadays, many different versions of coding has been developed, even to be very special codes just for different shape of piles. This one step tapper piles that work on offshore environments, because in this, I think in the 70s and 80s, there's a lot of motivations from the offshore oil market. That was the black money time, and a lot like the golden time, one of the golden time in geotechnical engineering, just because of the oil market is attract a lot of like resources, and because of that, so there's a lot of different like special coding for this particular topic. Power driven topics was developed at that time. And again, like around the world, there's many different computer code to develop, and everything starts from the wave equations. And actually, is many of the code or many like computations package available now. They use the concept of wave propagations plus the finite difference approach, the time steps approach. So which we kind of like walk you through, and then you try to you would try to do one quick example homework, and then I'll walk you through number wise on paper how to see the numbers work out. And there will be other methods too. We talk about the wave equations, and working on the wave equations, and on top of also coupling with the finite different time steps approach. Many different methods is developed. Is kind of like coupling with some simple instrumentations on field and calibrate your wave equations. That's what they try to do. So we will talk two more like methods, which also cover in your textbook. I think it's in your bureau textbook. One is the case method, another is the cap wrap method. We'll talk about those. First, the cap wrap method. So when this method is used, or by the way, those are not like a brand new method. Those are some improvement or some adjustments, modifications with additional instrumentations or additional informations on power driving, because like the wave method is kind of like the theoretical background, but it's not like precise enough to solve for the whole thing, or like or even not getting close. So people keep calibrating this kind of like a framework. So this cap wrap approach is one of them. You need additional informations, which is by using some strain gauge and two accelerometers. So when people like try to drive a piles, because at the beginning of the lecture, right, we look at some size of those piles. It's huge, which means expensive. So you won't hurt the budget much by losing or by embedding one or two simple instrumentations like accelerometers, or a strain gauge. Even though you put like accelerometers at the bottom of the piles, you never retreat it for each piles. That's fine, because those are very expensive. You're just using a one-time use instrumentations, not a big deal. But anyways, like you have the strain gauge, and also you have the accelerometers. Then you can calculate the force, because that gives you real-time measurements in the top of the piles. And you can, once you have the accelerations, and then you integrate it, you get the velocity by simple equations like that. And after you have an equation, velocity equations, and then like you do your math, you can back calculate the force, right? F equal ma, and the accelerations. If you do your math, you can put that in terms of velocity that you just calculate. So at the end of the day, your force is in terms of the velocity that you measure. So this part is what you measure, and the rest are like material properties, and the C is the wave velocity. So after you have those informations, then you can calculate the force. And this method is pretty much just like give you calibrations like a data. So you will, after you have your like kind of like a data recorded on in the field, and then you will keep calibrate your wave propagations analysis that we talked about previously. So those so remember those like a symbols like analysis that we have done. So you'll be keep calibrating those analysis, some parameters or some procedure, fine tune it until like your analysis results is matching the recorded results. So this is the big picture of the cap wrap method. So there's some like real data that people record from the field. So they have the power solutions and the measure the force. They try to like mesh the two. You cannot get like a perfect mesh, but you will keep iterate or keep like sensitivity, the parameter sensitivity analysis until you get one that getting the closest to. So you in a way that like is powerful because it keep you you have your theoretical base model, but now you have your field data. And then it allows you to do the calibrations based on site-specific pile difference record. The other method is the case method. So pretty much like you try to calculate the pile capacity based on the force and the velocity that you measure, and you also take care of the pile mass. So this is like the equations that they use to try to estimate the pile capacity. Again, this is the different pile driven capacity, the pile driving capacity, not necessarily the static capacity that that you estimate from an approach. So both the case method and the cap wrap method, I just want to give you an idea as like what's going on. And this is pretty much like a more advanced or more practical approach that people use. And and when you practice in this field, you realize there's a bunch of different methods, but more or less they are about doing the same. The concept is they try to get some real-time data right on site for your piles, and then calibrate the wave propagations model such that like you get a good match. So that last but not least, some summaries for this lecture. The wave equations that we talk about is much better than the pile driving formula, the energy-based pile driving formulas that we talk about very early in the lecture. So the wave propagations like a framework will be much better than those like pile driving formulas based on the energy conservations or some modifications come with it. This is not not accurate at all, put it this way. And the wave propagations is a great improvement, but there are still some like substantial difference between the wave equations predictions and actual values like the stress. Because the pile driving phenomenon or the process is a really complicated method, and the wave equations approach give you a good head start, but it's still really hard to explain or try to capture all the complicated factors you may have for piles to piles, site to site. And the finite difference algorithm, which is the time step approach that we talk about, will help us to getting closer to the answer. We have tried to do some very simple examples for you to see how things work out. And like for geotech engineers, we adopt like particular code, and then like and then like adjust the maximum allowable stress to reflect the local experience. So those are the other method we talk about, the case method, the also like the cap wrap method. Those are like many different methods to try to calibrate yourself or calibrate your models based on some measured data. And the whole approach highly also depends on the TZ or the QC response that we talk about, which is the quake, how much like a soils has mobilized both at the side and also at the tip of the foundations, the deep foundations. So that's why those TZ analysis that we taught in CE 467 serve as a very good starting point or very good fundamentals aspect of deep foundations that like you understand, how to modeling the pile, the soil structure or the pile soil response, or how to look at it, or how to like think of it as like a spring model that you can work on. And more importantly, even though all this effort that we use, the wave equations analysis, actually you are not like solving the actual static pile capacities. You are dealing with the dynamic pile capacity during the pile driving process. It's important, even though like it's not like the end product you want. But like you need to make sure your pile first. You need to make sure your pile survive the pile driving process. So a huge project, you could have a couple or even like a dozens, 2 dozens of piles to be installed. And the informations you get from very first piles could ensure your like success of the project, because the second, third, so on and so on piles, you can calibrate yourself, make sure like you won't overdriven the piles, which fail your piles right at the power driving or power installations process. And also like the dynamic capacity somehow is also related to the static capacity of the piles. So the informations that you get from pile driving process will help you a lot also on the static pile capacity analysis. Last but not least, like those like a cap wrap method, these are very useful, particularly the cap wrap. It will be useful because the instrumentations at top of the piles will help you to eliminate other like major source of error, including the hammer and also the cushions. Okay, welcome to CE 567 Geotechnical Design number 2. In this lecture, we will talk about pile driving and a couple of learning objectives. First is to introduce you to the topic of pile driving, which is very complicated, and it is one of the most advanced and difficult topic in geotechnical engineering. We will talk about the wave propagations in the pile driving, which is the best approach to solve or to like analyze the data we receive in this topic. And we will use a finite difference approach to solve for the wave or the setup for the wave equations, such that we can look for the informations we need. We'll talk about that more. And last but not least, this lecture will help you to understand the limitations of dynamic driving pile analysis. So here, give you a quick, just walk you through really quick, or give you a quick demo on pile driving. So you see we have the long piles here near shore, and I hope you can hear the sound. May not be doing so well, but the pong 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 sound, it comes from like you have a I believe this is a hydraulic hammer. You have all this like power or like oil cable from connect to another like a hydraulic actuator or hydraulic pump to this hydraulic actuator pounding on the piles. So the topic of pile driving we'll cover later is try to make use of the informations that we receive or like the data we record during this pile installations process and make use of those informations to recover the informations that can help us for pile design and also make sure during this pile design or pile driving process, we are not failing the piles. So this is what we need from pile driving. And the pile driving capacity that we talk is under dynamic conditions, which could be very different from the static conditions when you design the pile capacity that you have already learned in C467, the previous geotech class. The alpha method, beta method, those analysis or the homework that you just did, that was based on like a static capacity, but now is everything is dynamic during the pile driving. So this pile driving could be driving either like steel pipes or concrete piles. So this is concrete piles you're seeing, but more often we do it for the H piles, the steel H piles.